All right, so let's launch right into it. What does the formal model look like? Well, there are three ingredients we need to worry about. Who are the players? How we represent them? What are the strategies and payoffs? So let's start with that. Let's start with the players. So who are these decision makers? Well, let's take an example. When we're speaking about negotiation among countries, are we speaking about the U.S. as a single entity? Are we speaking about some political party or some office, the State Department, or about all the citizens? It's a decision we need to make as modelers, and that's the first thing we need to do. Once we do this, we need to decide what are the strategies that are available to them. Every model captures some information, not others. So, for example, is speaking about active versus passive enough to capture everything we want about the relation between predators and prey? Well, it's up to us about what we want to model. And the same goes for all other elements of modeling. So here are the elements of the normal form. First of all, we start with a set of players N, consisting of some number of players, which we denote 1 through little n. Each of the players has a set of actions available to it, which we denote by A sub I. Player I has a set of actions, capital A. A action profile, which we denote by capital A, is simply the Cartesian product of the individual action sets. So the vector little a1 through little an, the action profile will describe which each of the agents, which actions have each chosen. Finally, we need to say what agents care about, and that's where the utility function comes in. The utility of agent I, denoted by u sub I, is a mapping from strategy profiles, that is, from the choice of action by each agent, a mapping from that to the real numbers. So let's look at our predator-prey example, and we already saw that we have two agents, the predator and the prey. The strategy profiles, the strategy sets for each of the agents are identical, consisting of two actions, passive and active. And similarly, the utility functions for agent 1, for example, the utility for for the predator when he is active, and the other agent active is 2. So let's look at another example. We might call this a collective action game. We have citizens, 2 of them in fact, and they each can decide whether to participate in a revolution or not. If they both participate, then all is good. Their revolution is successful and they get some positive payoff. If they both decide to stay home, nothing of note happens. However, if one of them revolts and the other not, for example, this way, then the revolutionary fares very poorly, and again, the person who stayed home, nothing of note happens to them. That's our game. How do we model this? Well, as you might expect, we have again 2 players, 1 and 2. It happens to be again symmetric. They can revolt or not. If they both revolt, the payoff is 1, and so on. So hopefully this is pretty straightforward. There's one thing that bears speaking about. We have these numbers in these matrices. What do they represent? What do they capture? So, for example, imagine my playing a game of poker. Do I care only about what happens to me? And when I speak about what happens to me, am I speaking about only the money I made or lost, or some other aspects? What about the other buddies around the table? Could it be, for example, that I actually care that they do not too badly. Well, maybe in poker, one of them is my friend and I care about that. Or maybe I'm very competitive. I actually don't care how much I made so long as others made less, and so on and so forth. Perhaps there's some games where I care not only about how much individuals got in and of themselves, but some overall mix of the payoffs. I have some notion of fairness in mind. Whatever it is that your notion of payoff is folded into that number. There's much more to speak about it, but that's how you should think about it. Everything I care about, everything the agent should care about, is folded into that number. So we now know how to represent games. How do we analyze them? This gets us into the notion of solution concepts and essentially much of game theory. So we've seen that any matrix defines a game more precisely. Every matrix in which in each cell we have as many numbers as there are players, one payoff for each of the players. We sometimes, in the case of two players, call these bimatrices, which you can view really as two matrices, one for each of the players. That's a very large space of games, and to get a sense for it, we can look at two specific classes of games. These two classes can be thought of capturing the extreme points on the spectrum of competition and cooperation. The class of team games are the ones that describe the most cooperative situations you can imagine among agents, whereas the zero-sum games capture the other extreme of extreme competition. Let's look at those in turn. So here is the canonical pure coordination game. This is the game in which we walk toward each other on the sidewalk, and we can each either go to the left or go to the right. If we both go to the left and both go to the right, all is good, we pass each other. But if we happen to miscoordinate, we bump into each other. And we are all familiar with this situation where sometimes we engage in this dance where we both go to the same side and collide and jump to the other side until eventually we manage to pass each other, which is why it's sometimes called the sidewalk shuffle. From the formal point of view, the games are defined as follows. The most straightforward way to define it is to say that for any possible action profile that is ever really cell in the game, each of the players get the same payoff, which is what we saw in the previous example. In fact, this is too restrictive because really it doesn't matter that I get exactly the same payoff as you do so long as we have the same preferences. And in other words, it doesn't matter if I get $1 and you get $2. If it so happens this is the highest payoff for each of us, that's good enough. More precisely, we need to speak about having the same preferences over all the mixed strategy profiles or over all the lotteries, over strategy action profiles in the game. And so the full definition is the following. It says that for any two strategy profiles, S1 or S2, that is any two strategies, one for you and one for me, I prefer the one mixture to the other, just in case you do as well. That means our interests are completely aligned, and that's a game of pure coordination, or a game of pure cooperation, or a common payoff game, or a team game. These are all named for the same sort of thing. Let's now look at the other extreme, and these are zero-sum games. These are games of pure competition, and here are the two very familiar poster children for that class of games. Matching pennies is a game where we each need to choose heads or tail. If we match, that is, we both chose heads or we both chose tails, then I win, otherwise you win. Rock, paper, scissors, or Rochambeau is the famous, familiar children game. As we know, rock beats scissors, scissors beat paper, and paper beats rock, and the game is written down right there. From the formal point of view, the situation is also fairly straightforward. We limit the discussion to two-player games, and in a moment we'll say why. We require for each of the two players the payoff sum to zero. That is, the payoff of one be minus the payoff of the other. And now we can say why we restrict ourselves to two players, because when you think about it, any game of a general sum game with no particular properties can be turned into a zero-sum game with one additional player. One way to do it, and perhaps the most straightforward, is give just a single strategy for the other player, so they really don't participate in the strategic aspect of the game, and assign the payoff to them is simply minus the sum of the payoffs of the other players. So really, as a category, that's not an interesting category unless we restrict ourselves to only two players. Here's another point, and this is a very important point, that zero really does not play any particular role here. You can take a game and perturb all the payoffs by what's called a positive affine transformation. That is, either multiply all the payoffs by some positive constant, or add a constant to all the payoffs, and a constant that's positive or negative in this case, and the game really has not changed at all. And so in particular, you could take the zero and add a constant to it, and nothing has changed. And so when we speak about zero-sum games, we really mean constant-sum games. These zero-sum games are sometimes called games of pure conflict or pure competition, sometimes adversarial games, really the same sort of animal. These are really the games that were studied most in modern game theory in the middle of the 20th century. And we will be returning to them later.